Hi everyone, in this video I am going to go over the quotient rule. So this is the second part of section 3.2. And again, one thing that's going to be important to notice is just which technique you can use and when. So there will actually be some equations, some functions that you can use either the product rule or the quotient rule on. There are some that you must use the product rule, some that you must use the quotient rule on. So I'll talk about that a little bit, but mostly just wanted to introduce the quotient rule and give some examples. So the quotient rule is what we use when we have two functions that are divided, right? So the quotient rule tells us that for differentiable functions f and g, okay, so one for f of x over g of x, or f of x divided by g of x prime, meaning you're taking the derivative of those two things divided. Okay, you'll have f of x prime times g of x minus f of x times g prime of x all over g of x all squared. In other words, how I typically say this verbally is the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared, right? So just like the product rule, if we were to prove why this equation is true, which I'm going to spare you from on this, but feel free to ask during office hours or look it up if you're curious on the proof, it would work kind of similarly to the product rule proof. We would have to go through that longhand limit definition of a derivative and do even more algebra and simplification to get us to the point where we had this rule peeled apart. All right, I'm going to also write this in the Leibniz notation. So the way we would write this in Leibniz notation is that we have d dx, so the derivative of f of x divided by g of x, right? That's equivalent to the derivative of the top, so d dx of f of x times the bottom, so times g of x, minus the top, so f of x times the derivative of the bottom, so d dx of g of x, and then all of that divided by the bottom squared, so g of x all squared. Okay, so again, I recommend just saying this verbally as you go through: the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared, and also take note of the form of the first function you start with so you know what you should use. Okay, so let's do at least 2 or 3, maybe more examples of this. Let's suppose that we have f of x equals e to the x divided by x squared plus 1. All right, so remember in the last video when we had two functions divided, we used the nice little trick of just changing the exponent of the denominator so we could use the product rule. All right, if we try to do this right now, and I'm going to erase this, but if we try this, we'd have, all right, f of x is equal to e to the x times x squared plus 1 to the negative 1 power, right? Because this denominator is to the first power. Okay, so we could write the product rule out for this. The issue is this right here. Okay, on this you have a whole function, x squared plus 1, raised to a negative power. We don't have a technique for that. That's technically called the composition of functions because this function is fitting inside of this function. We don't have the technique for that. So if you try to use that little trick of pulling the denominator up, it's not going to help you because you won't be able to fully use the product rule to take the derivative because we don't know how to take the derivative, at least with shortcuts of that type of function, and it'd be pretty tedious to go through all of it longhand. All right, so this means, you know what? When I read this, I have e to the x divided by x squared plus 1. I'm going to have to use, at least for now, the quotient rule on this one. So since this is starting in prime notation, I'm just going to write it in prime notation, although I'm comfortable with you using whatever you're comfortable with for now. At some point, you'll have to get used to the Leibniz notation. All right, so I have f prime of x equals, I want to use the quotient rule, so I'm going to take the derivative of the top, and my top function, just write this as top, okay, is that, and then my bottom function, it's a really informal way of saying it, but sometimes it's helpful to just think of it in layman's terms. Okay, my bottom function is x squared plus 1. So if I take the derivative of the top, that is really e to the x prime times the bottom is times parentheses x squared plus 1 minus the top is e to the x times the derivative of the bottom is x squared plus 1 prime. And then we have all of that over the bottom squared. So x squared plus 1 all squared. All right, I haven't completely taken my derivatives yet. I still have these little primes in here, so let's take care of that now. The derivative of e to the x is the derivative of e to the x is e to the x. So I have e to the x times, I'm just going to rewrite the x squared plus 1 minus, rewrite the e to the x. Okay, now I need to take the derivative of x squared plus 1 prime. So since this is added inside, I can take the derivative of each part separately. The derivative of x squared is 2x, and that is because of the power rule, since I have a variable raised to a constant, and all of that is still divided by x squared plus 1 all squared. All right, so honestly, you could just leave your answer like this. It's clear what you did. I'm fine with this answer. As I've stated before, sometimes in the book, they're going to make you simplify these. They're going to make you write it differently. If you, so I should say with WebAssign. So if you do WebAssign, you're going to have to probably do more algebra, as I've already described a couple times now. All right, so let's move on to another example. All right, this time we have g of t is equivalent to t squared minus 1, and we're going to calculate dg dt. All right, so on this one, it looks like we're in Leibniz notation. I'm going to stick with Leibniz notation. If I tried to write this as a product, I'd run into the same problem I did last time. So I'm not going to do that. I am going to use the quotient rule. All right, so by the quotient rule and with the Leibniz notation, I have d dt of 1 over t squared minus 1, oops, there we go, is equivalent to, all right, notice your top function is just t. All right, and your bottom function is the t squared minus 1. All right, so going through that quotient rule, I'll write everything out. I'm going to have the derivative at the top, and in Leibniz notation, that'd be d dt. Oops, I didn't use the same color, sorry. All right, there we go. Make this match. And I really hope you can't hear the talking in the background. I'm sorry, my boyfriend's family is also very into politics, and they seem to be having an intense political debate right now that I'm really hoping nobody else can hear. And I guess when you have those, you simply can't be quiet. So I don't know. I asked. Okay. So anyway, derivative of the top is t prime. Shoot, forgot I was using Leibniz notation. So the derivative of the top is d dt of t. Okay, times the bottom is times t squared minus 1 minus the top is t times the derivative of the bottom is d dt of t squared minus 1. And we're going to put all of that over the bottom squared. Okay, so we have t squared minus 1 squared on the bottom. All right, now we have to actually take our derivative. So if we take the derivative of t with respect to t, that's just 1 by the power rule, right? Which means we have 1 times t squared minus 1. Not really necessary to write the 1, so I'll just write t squared minus 1. Okay, carry our minus t, so that's this part right here. Okay, now I need to take the derivative of t squared minus 1 with respect to t. I can take the derivative of two functions subtracted separately. So the derivative of t squared is 2t by the power rule. Since I have a variable raised to a constant, the derivative of negative 1 is just 0, right? And then all of that is divided by t squared minus 1 squared. Okay, again, this answer is fine. This one is extra sloppy looking and pretty easy to simplify, so I'm going to simplify the top a little just to make it look nicer, although honestly, if your notation is clear, I'm okay with you leaving your answer like this. I just don't like to leave it real sloppy looking. So first I have the t squared minus 1. Okay, t times 2t, that's pretty easy to multiply. We get a 2t squared. Okay, and then I might as well do just the basic parts of this, and that's to combine like terms. So t squared minus 2t squared is a negative t squared minus 1 over t squared minus 1 all squared. Okay, so I just simplified that because the numerator was pretty easy to simplify. In the text, sometimes they'll really take it far, and you'll have to do some pretty complex simplifications, especially if you use WebAssign, but I generally just try to make it look nice, but honestly, even if you stopped at this second step, it would have been okay with me. Okay, so I think that this concept, this idea is enough to get you through section 3.2. You now have the product rule and the quotient rule, which is what you need for that section. And like I've said before, some questions will be more tough, some will be less tough. The key thing is to make sure do your work promptly and leave yourself enough time to get help and ask questions if you have them. Other thing I wanted to note is that in this section, they asked you to take second derivatives. All right, a second derivative is really, maybe I'll write this out a little bit. The second derivative is really just the derivative of a first derivative, which I think you've actually seen at this point, but let's do a quick example. If I have f of x is equal to 3x squared, my first derivative, is going to be 6x. My second derivative will then just be the derivative of the first, so that's 6. So the main thing I want you to keep in mind is I highly recommend simplifying your first derivative if you have to take a second. So as I stated before, I'm not super picky on the simplification stuff unless you have to apply it or use it, and that's because when you simplify it just makes it easier on yourself. All right, so please give the homework a try. Come to office hours this week if things don't make sense, and then I hope get on top of 3.2 real quick so then you leave yourself enough time to study for the exam. All right, thanks.